Statistics Part 1. Hello everyone, welcome to Lecture 1 of Statistics. This lecture is an introduction to the key concepts in statistics and an explanation of why in the rest of this 12-lecture course we will be looking at methods of sampling theory statistics to answer questions where we need to learn from data. Okay. So these example questions may help to explain why we need statistics as a field of study. So these questions come with a story. So imagine in this story you are looking at an exam paper, and the exam paper asks you to choose one of the following questions and answer it. You only have to choose one. Each of these questions is just worth 1 mark. Your choice of questions is this. A. You have 343 small cubes, each with side length 1 centimetre, and you arrange these into a single large solid cube. What is the side length of the larger cube? Alternatively, question B. Among patients with a particular illness, 100 are given no treatment, and 68 of those have a good outcome. In other words, they completely get better. Another 100 patients are given a drug, and 73 of them have a good outcome. Question: is the drug beneficial? Alternatively, question C. You meet a nice couple from the town of Lake Wobegon, Minnesota. Are most couples from Lake Wobegon nice? Which of those questions would you choose to answer? You're welcome to stop and think about that. But if you do, I'm sure that you will have a good taste for a correct choice of exam questions, and you will say, I'd probably like to answer question A about the cubes. The answer is 7 centimetres for the side length of the big cube. And the reason I would choose to answer that one is because once I've written down 7 centimetres, I know that this is certainly the correct answer, and I know that my answer is complete. There's nothing more to say about the subject. By contrast, if I answer, say, the question about the drug treatment, I could say yes, which would be a complete answer. There would be nothing more to say if I simply said yes, the drug is beneficial. But the answer is, of course, not necessarily true. Maybe it happened for some reason by chance that more of the patients given the drug got better. Perhaps they weren't as sick to begin with, and we didn't know that. So really then, if I want to give an answer which is definitely true, I could say for question B, possibly. But then that doesn't seem like a very complete answer. In general, people like to give answers to questions which are certainly true and complete. And the subject of statistics is a scientific way of giving an answer which is as true and complete as possible to questions which involve uncertainty. If you travel around the world, you can probably find many different ways of answering questions which involve uncertainty. But in this course I want to do an introduction to 3 scientific methods, which are going to be sampling theory statistics, Bayesian analysis, and machine learning, and then I will explain why in this course the valuable one for us to look at is sampling theory statistics, or classical statistics. Okay, so that is an introductory question, but don't just take my word for it that methods for dealing with uncertainty are valuable. Take the word of someone much more influential, James Clerk Maxwell, the legendary Cavendish professor of physics. Now, he said in the 1800s that the actual logic of science at the moment is conversant only with things which are either certain, impossible, or completely doubtful, and none of which, luckily as it happens, we have to reason on at the moment, he said. Just to explain this, when Maxwell says the science of logic, he really means deductive logic, so essentially Aristotelian logic. For example, reasoning of the type that all Labradors are greedy. My dog is a Labrador, therefore my dog is greedy. So that is something where if the premises are true, if my starting points are true, then the argument guarantees that my answer is also completely true. And that kind of deductive logic is perfect if what we want to do is make pronouncements on things which are completely certain, like the greediness of my dog, or completely impossible, like the abstemiousness of my dog, or when he says entirely doubtful, he means possibly true or possibly not true. Maxwell goes on to say, therefore, the true logic of the world, the one which is needed in physics, he means, is the calculus of probabilities, which takes account of the magnitude of probability which is, or ought to be, in a reasonable man's mind. He means, I think, the degree of belief in some statement, not degree of belief in the statement, my dog is greedy, for which I have absolute certainty, but degree of belief in the statement, for example, that the drug in example question B previously was beneficial. So Maxwell says there's an important need for probability theory and for the science of statistics, and he had a lot to say on the subject. I won't talk more about Maxwell and statistical mechanics, but I will say I like this slide because it gives me the opportunity to tell my favourite story about James Clerk Maxwell, which is that when he came to Cambridge for the first time, he arrived at, I think it was Peterhouse College, and he was told on arriving by the porters, hello, Mr. Maxwell. You might like to know, since you've just arrived as a new student, that there'll be a church service tomorrow morning to welcome all of the new students, and that will be at 5:30 a.m. if you'd like to attend. And Maxwell replied to this, 5:30 a.m.? I guess I could stay up that late, which I think shows the good spirit, a good energetic spirit of enthusiasm for taking part in his life at the new university that he'd come to. Okay, anyway, so that's my favourite slide because I get to tell that, which is the best story about Maxwell. Now, what about the layout of this course? So in this course we have 12 lectures, we have 9 chapters of lecture notes, and then we're going to start by looking at this concept in statistics, and we'll work through probability theory, and we'll talk about learning about true underlying physical fact by studying data, and then we'll look at hypothesis tests. These are ways to make statements about questions which involve uncertainty, but the statements we're going to make are going to be as complete and certain as possible, and then we'll finish off by looking at linear regression. Okay, the recommended textbooks for this course. So the one for this course is Ross, Introduction to Probability and Statistics for Engineers and Scientists, 2009 edition. It's also worth having a look if you like online course material in addition to textbooks. Although Ross's textbook is very good, it's well worth having a look at this website which has an introduction to probability theory and statistics. The website is at the worryingly named www.randomservices.org. So if you follow that link, then they have actually very good introductory material on probability theory, which extends a bit beyond the scope of this undergraduate statistics course. So those are the recommended sources I would look at for this course. Further reading is not something that I would expect you to look at for this course, but all of these 5 textbooks I've written down here are absolutely excellent. For the first 3 as well, you can easily obtain the PDFs online. I think they're all deliberately publicly available for free. And those textbooks are, so I've said, Hasty's textbook on elements of statistical learning. That's a machine learning textbook in large part, but it has chapters which are a very good review of conventional sampling theory statistical methods, and it's an exceptionally well written book. All of these books are beautifully well written, and elements of statistical learning will be valuable for people who want to go a bit further and use computational methods to apply statistics to the real world, and to analyze their data. Book 2 of my recommendations is David Mackay's Information Theory, Inference and Learning Algorithms, an absolute classic, a book which keeps on giving. You can often come back to, well, I can often come back to this textbook and find another chapter with some really brilliant comments on Bayesian analysis, and as well as machine learning, which I had not previously known that I even wanted to know about. But his book is outstanding, and his course on inference is also available as online videos. Also from the year 2003, Edwin Jane's Probability Theory, The Logic of Science, which has a title, The Logic of Science, inspired by that previous quote from James Clerk Maxwell. This is a fantastic book on the philosophy of probability, and in particular the philosophy of the Bayesian approach to data analysis. This course is not on the Bayesian school of thought about data analysis, but Janes's book is absolutely fantastic to think more about what it is we're doing when we're trying to learn from scientific data. A couple more textbooks to recommend, also on Bayesian analysis. There's Jim Stone's Bayes Rule with R, a tutorial introduction to Bayesian analysis. This is a pretty friendly introduction textbook to Bayes theory. Actually, my favourite ever book on Introduction to Bayesian Analysis is Donald Berry's Statistics, a Bayesian Perspective from 1996. The only problem with this is that it seems to be out of print. It's relatively hard to get hold of, but it is the best introduction I've ever read in a textbook to Bayesian inference. Something to say about these books, all of these books on stats and probability theory that I would recommend, they're all new. And this is unusual for a course that I teach. Normally there are classic textbooks which are relatively old, and I'm happy to recommend them. For example, in corrosion, I happily recommend Fontana's 1970 textbook, which is in many ways the genre-defining textbook for its course, and remains a classic and still valuable. In fact, for statistics and probability theory, modern computers have made so much progress, they've so effectively brought on the subject, that the modern textbooks which take advantage of good computational approaches actually are profoundly better, in my view, than previous books on statistics. So you could read for reference, you could certainly read Ronald Fisher's Statistical Methods for Research Workers or Design of Experiments, but in my view these new textbooks are simply beautifully written and more useful for modern practice, and, well, honestly, they also avoid some of the controversy which many of the 20th century textbooks were mired in the war between the Bayesian analysts and the sampling theory statisticians, which is now not so much of a controversy. People are just happy to read about the different schools of thought. Okay, key concepts in statistics. So we'll start with chapter 1 of the handout. We said we are answering questions in science which might look like any of these questions, 1.1a through 1.1c. And the cube question 1.1a has a straightforward answer, 7 centimeters, which is certainly true and complete. That gets a smiley face because people like that kind of answer. This looks like we have finished our scientific question. Questions B and C involve learning from evidence, but we have a question which concerns uncertainty. So in the question about does the particular drug work, the answer yes is not necessarily true, but the answer possibly, although it's true, is not very complete. Statistics gives us a scientific way to answer questions about data where we have to deal with uncertainty. Actually, let's give some definitions from the dictionary to start with. Statistics as a field of study, if we just look this up in Merriam-Webster, the word statistics meaning a field of study, the first of its meanings is a branch of mathematics dealing with the collection, interpretation and presentation of masses of numerical data. I would summarize this a bit more. I would simply say statistics is the science of handling data. But the Merriam-Webster definition is a bit more precise, and there's something I find pretty amusing about it, which is that dictionaries are written mainly by English literature graduates, or people who are experts in the English language. Something to be amused by is that these arts graduates, you can see from their definition of statistics, when they describe about presentation of masses of numerical data, you can see they implicitly understand this is something for them which is quite scary. So it's not just the presentation of data, which is what I'd say, but it's data which comes in masses, which sounds clearly terrifying. Actually, something to take away from this course is that there should be nothing alarming or frightening about dealing with data. We don't have to have the same fear which the English literature graduates have given away in their definition when they talk about the terrifying hordes of data marching towards them. Nonetheless, so notwithstanding that it gives away their attitude towards the scariness of doing mathematical analysis of data, the way they describe statistics as a branch of mathematics is a beautiful definition. And given this definition, 1.1d, it's actually clear to us that questions like 1.1a involving the cubes might appear in statistics. For example, if I just want to present some data to someone and I tell them, I've got loads of cubes in a box, and this person, my friend, asks me, how many cubes have you got? I could answer, give me a minute. I've got enough cubes to make a single large solid cube with a side length of 7 centimeters. And that would be a task in which I've interpreted and presented data, so it would be a part of statistics. But nonetheless, it's questions like 1.1b to c, which involve learning from evidence when the conclusion is uncertain. Those kinds of questions are the ones which provide a need for a whole branch of mathematics. The cube question is quickly dealt with. You just need to know what a cubed root is. The questions where we learn from uncertainty, this is why we need a whole new field of study. Let's have some more definitions. So section 1.2, deduction and descriptive statistics. So, while the most influential results from statistical analysis are conclusions about something uncertain, so for example, a prediction about the future, the simple task of presenting gathered data is also important. And the task of presenting and summarizing data can be done using methods which make up the field called descriptive statistics, and tasks performed using descriptive statistics actually often do not involve any uncertainty. The task is deductive. Deduction means the process of reasoning from one or more statements or starting points or premises to reach some logically certain conclusion. For example, that my dog is greedy. Now, if we have some example data, for example, all of the scores which Alistair Cook has ever scored in test matches, and if we know we've collected the data and we know he had 291 innings, of which 16 were not out, and he scored in total 12,000 and something runs, we can calculate a descriptive statistic, which is his batting average, 45.35. And there is no doubt about this conclusion. It is logically certain. I have deduced it from the list of scores which he made, or I could have deduced it from the list of scores he made in his test matches. Another statistic is that his current age, it says, is 33 years and 312 days. So there we are. There's no doubt about that. This means there's another use of the word statistics. So definition 2 refers to numbers. A statistic as a number is something which summarizes the result of a study. So, for example, a batting average. In the field of study statistics, task number 1 we have to do, in order to avoid making mistakes, is we have to always be very clear about whether we're dealing with descriptive statistics, which involve certainty, or the other kind of statistics, inferential statistics, where we are drawing conclusions about something uncertain, for example, making predictions. In fact, this distinction between definitely true descriptive statistics and possibly true interpretations or predictions is at least as important in the real world as it is in mathematical questions. For example, in the real world, I might come across conflicting news articles, and I might struggle to understand how to reconcile these conflicting opinions. And I can do so, I will be able to do so, as long as I keep clear the distinction between descriptive statistics and inferential statistics. Here's a couple of, on this slide, conflicting news articles. Both of them contain a descriptive statistic. On the right-hand side, we have a graph from the BBC in an article entitled "Which Form of Renewable Energy is Cheapest?" And in this graph, we have the total cost, it's called in this article, total cost. They mean levelized cost, which is a more technical thing, but they say total cost per megawatt hour for producing electricity by various different methods, and they compare offshore wind, which is quite expensive, with solar electricity, which they claim in large scale is quite a bit less expensive, and they show onshore wind, which turns out in their graph to be the lowest cost of the different sources of electricity, including combined cycle gas, which is a fossil fuel source of electricity which they claim is slightly more expensive than onshore wind. So that's one graph, and a conflicting article we find on the left contains some more descriptive statistics. The left-hand side graph is a scatter plot showing on the x-axis the percentage of electricity in various European countries generated by renewable sources. It says wind plus solar, so for simplicity we can read this as mainly wind. And on the y-axis we have euro cents per kilowatt hour, the average domestic electricity price in those countries. And on this graph we have a scatter of points, but there is a fairly convincing trend that the larger the fraction of electricity generated by wind plus solar, the higher the electricity price. And the trend is actually quite steep, so that if you have this trend line and you consider that it's 0% electricity generated from wind and solar, that means a domestic electricity price of about 12 cents per kilowatt hour. Once you get up to 25 or 30% electricity generated by wind and solar, that gives you 25 euro cents per kilowatt hour. So in other words, according to this trend line, for every 25 or 30% of the electricity in a country generated by these renewables, the domestic price of electricity increases by 100%. So this seems to strongly imply that wind or these renewable electricity sources are in fact much more expensive than the old-style fossil fuels which they are replacing. So how do we reconcile this? The way that we need to approach this is to realize both of these graphs are descriptive statistics. They have been put together by collecting data and presenting it. What we have to be super careful of is not to then immediately accept the interpretation put next to it, which is an inferential process, a possible interpretation. I will talk about these graphs more in Lecture 2 to present the importance of making cautious interpretations. For now, I will say that the BBC's graph, which describes these things as total costs of electricity, is the more misleading interpretation available in these two stories by far. But I will return to that later, and I will discuss the problems of reaching conclusions about the real world, even if you have numerical data, descriptive statistics, about which there is not much doubt. Okay, inferential statistics we'll just introduce as a concept at the moment. We probably, just you can see from those graphs, it can often take a huge amount of effort just to collect numbers and to summarize it using descriptive statistics. And it's actually only once that work is done, the second task can get started, so using inferential statistics to make statistical inferences. Statistical inferences, for example, does a particular drug improve the health outcome of the patients given this drug, have two key characteristics. Number one, experimental or observational evidence is available for us to reach our conclusion, but feature two, the conclusions are not certain in general. A couple more useful definitions of these. Statistical inference. This is extrapolation from a sample to information about the population being sampled. In other words, looking at a bit of data, some numbers which we've observed, and making conclusions about the physical world. A special case of inference is prediction. which is where we want to make an inference not so much about the true status of the physical world now. Instead, we want to make an inference, an extrapolation from the data to information about the next sample which we have not yet observed. There's this sketch just to summarize the idea that inference is where we have some known sample of data and we're trying to estimate things about the population. And then prediction is if we know the population, we're wanting to draw inferences about the properties of some future sample that we have not yet seen. Prediction and inference are a pretty important set of tools in physics because one of the key ways that equations are used in physics is to relate underlying physical truth or parameters with what we observe or data. And those equations can be used both ways. For example, in the physics of a microscope, you might have an equation relating the structure of some object that you want to look at, so the physical parameters, with the image data which you observe. And if in some example piece of work, the parameters of the object which you're looking at are really simple. So let's think about a spherical fluorescent shell which just has one parameter, a radius a, describing the object. And there's a second parameter, a blur radius sigma, describing the microscope. We might have an equation which relates those parameters and allows us to take those parameters a and sigma and predict the image that we would observe of this object. Then in the other mode, inference, we could take the image of a specimen which we know is a spherical fluorescent shell, but it has unknown radius a, and we could infer the parameters of the underlying physical structure by fitting the equation to the image data that we actually collected. So those are prediction and inference. Now, in data analysis as a big subject of which statistics is a part, we might actually come across different schools of thought about prediction and inference, or let's say schools of thought about inferential statistics. This course is going to look at sampling theory statistics, but before we do that, I want to review some of the other approaches. I think there are three overlapping schools. So, school of thought number one is Bayesian analysis. This quote from Steve Gull perhaps describes Bayesian analysis perfectly. It is simply that what you know about something after your data arrives is what you knew before, plus what the data told you. Now, Bayesian analysis is a way of doing that adding up of information. The second school of thought is sampling theory statistics. The maxim for this field is certainly Ronald Fisher's statement, "Let the data speak for themselves." The idea is that what you knew before the data arrive should not really be colouring your conclusions that you're drawing, because you should try to find some way to be as objective as possible. That's sampling theory statistics, also called frequentist statistics or orthodox statistics. A third school of thought is machine learning. This is a more recent approach to data analysis. So we have this quote from Brad Efron. He says, "A third front seems to have been opened up in the long-running frequentist Bayesian wars, opened up by the advocates of machine learning, who don't really believe in any inferential school." I'll describe a bit more what he means by that to help clarify my understanding of the difference between these schools of thought on learning. Okay, so consider this example task to look at the different schools of thought. So imagine we are watching a game of snooker. So imagine we turned on the television, we were hoping to see Star Trek, but unfortunately it was cancelled because the BBC has to fill up its quota of live sport. So instead they've put on cheap, long-running snooker. And okay, so we're enjoying watching this snooker game. And during a particular game, we just see the start of the break. We see half a second of video as the cue ball strikes the pack of red balls, and they start to break apart. And then after half a second of them all moving, the television cuts out. Disaster. We don't know what's going to happen in the game. So if we wanted to predict or to tell for ourselves where do all of these balls end up, there's a few different ways we could do it. In two particular strategies I'm going to call physics and machine learning. Now, the first one, physics, which is also called by machine learning people data modeling, involves looking at the video of the start of the snooker break, and we want to use this video to estimate the ball positions and velocities at the end of the video. And given the positions and the velocities and some other parameters we might learn about, like the bounciness of the cushions and the coefficient of friction of the cloth, and maybe we could also work out from the video data to what extent each ball was rolling or sliding. So given these physical truths, positions and velocities, we could forward simulate from the end of the video data using Newton's laws to work out where all of the balls come to rest. And I have no doubt as a physics graduate that this would work in principle. It would be a pretty boring analysis, but we could do this. We could do this process of estimating the physical state of the snooker table, and then extrapolating forwards what will this state turn into because of the known laws of physics. In practice, this would not be the most exciting use of our time ever, and we could probably have another approach. We could use machine learning, which is the school of thought which says we can make a prediction about the final state, where the balls end up, based on experience. For example, maybe I've seen exactly the same break before in the past, in which case I know where all of the balls are going to end up because I'm just duplicating it. Alternatively, maybe I have not seen this exact break before, but I've seen something which looks like the left-hand side of this break before, and in a different game I've seen what the right-hand side looks like, and I know where those individually end up, so my prediction for where the balls end up this time might be some weighted average, some agglomeration of where I have previously observed the balls ending up. So this is machine learning, also called algorithmic modeling. Let's look at a couple more slides to tell a bit more about these schools. So Bayesian analysis, we are dealing with inference by talking about information. We're combining our prior information with something that we've just observed for some data. The big strength of Bayesian analysis is that it allows us a logically coherent way to do inference, and it's actually a very natural way of reasoning. There are some situations where it simply is absolutely true that if I want to know about the world based on a little bit of experimental evidence I've just seen, my final conclusion is going to be very largely filled in by my pre-existing scientific knowledge. One statistician who believed this is an important fact was a man called Joseph Bertrand, who collected these examples of two situations where you might collect very identical looking data, but a good scientist would reach completely opposite conclusions because their conclusions would be largely controlled by pretty good pre-existing background knowledge which they already possessed. And his example was this. So he said, question number 1, shipwrecks in Cornwall. He was measuring this, I think, during the 1800s. So a review of shipwreck dates and the weather conditions when the shipwrecks happened found that sailing ships were wrecked on the coast of Cornwall at a much higher rate than when the wind was blowing from the west. Should we expect this trend to continue? So a reasonable scientist would probably look at this and say yes, because I know where Cornwall is. I know that when the wind is blowing from the west, that means that there's wind from the Atlantic, quite possibly Atlantic storms, blowing ships towards the Cornish coast. So of course that's when you're going to have the most shipwrecks. Then this next example, deaths in Saint Malo. Saint Malo is a city in northwestern France, and the inhabitants, according to Bertrand, report that the local death rate there is higher on days when the wind is blowing from the west. Significantly higher, they say, than on other days. Should we expect this trend to continue? Oh, by the way, the death rate, we're just talking about people living in the city and maybe passing away from old age. And Bertrand says, well, this is obviously a complete superstition. There's no physical reason why the wind blowing from the west, as far as he could tell, would cause people to be more likely to pass away. So in fact, he says, well, there's lots of cities, this is just one where by chance this trend happens to have been observed, and no, I do not expect it to continue. So there's a question, does my knowledge of a physical mechanism in the world change the certainty we should have about some conclusion? The Bayesian analysis answer is very much yes. The sampling theory statistician, by the way, says basically no, except that our background knowledge might control our choice of what sort of mathematical test to apply to the data. We might apply a stricter test in the case of the St. Malo deaths before we would be convinced of the truth, but we would not simply allow our conclusion to be dominated by our pre-existing belief. We would instead have to collect more data. Now, this is really the key thing of sampling theory statistics, the idea, let the data speak for themselves. The idea is that you have to invent standardization in your scientific method so that you're able to do repeat experiments. But once you can do repeat experiments, you have plenty of data, and sampling theory statistics is all about taking plenty of data and inventing estimators which take that data and use it to make conclusions about the real world. You can also do hypothesis tests on is some theory correct. The big strength of sampling theory statistics is it's very good at model criticism. For example, if I want to ask, is the standard model of physics correct? I would find that personally very difficult to answer using a Bayesian analysis, because in order to say if it's correct, I would have to have some idea about my degree of belief in alternative theories of physics, and I don't know any alternative theory of physics. I'm not saying I perfectly understand the standard model of physics, I'm just saying I have radical uncertainty about the alternative hypotheses. As a result, it's difficult or even impossible for me to take my pre-existing radical uncertainty and add that to something I learn from some data to reach a final opinion. Sampling theory statistics, on the other hand, has no such problem. I don't know maybe an alternative to the standard model of physics, but I can perform some repeat experiments, and then I can apply a hypothesis test, and if the results of the experiments were quite far from what the standard model predicted, then I can criticize or maybe even reject the idea that the standard model of physics is exactly correct. And I can do that fairly objectively by, quote, letting the data speak for themselves. The weakness of sampling theory statistics is that it does need good experimental design so that you actually have repeatability in order for this data to be applied in this way. Your prior information, your background knowledge of some scientific subject does actually come into sampling theory statistics, but it does so by making the experiment repeatable in some way. And furthermore, another weakness of sampling theory is that by willfully ignoring our background information, we would perhaps make poor conclusions in some case. We might not be able to reach a judgment on the Cornwall shipwrecks and the deaths in St. Malo, which, using Bayesian analysis and being happy to use prior information, we easily could have learned about. Okay. School of thought number 3, machine learning. So from Leo Breiman, an advocate, an important machine learning scientist, he said, if our goal is to use data to solve problems in the real world, he means, then we need to move away from this dependence on data models. By data models, he means models of underlying physical truth. He says, we can't always have these models, therefore we need to adopt a more diverse set of tools. So what he means is that in, for example, the study of the effectiveness of drugs, we don't have a complete theory for whether or not drugs work, because we don't perfectly understand everything that happens inside different people's cell biology. But that's okay, because we can use previous experience of how well a drug has worked to make predictions of how well it will work in the future if we give some dose to a patient with some particular state of health. The difference between machine learning and sampling theory is that we're using plenty of data for both. It's just that in sampling theory statistics we're normally estimating underlying physical truths, like positions and velocities of snooker balls. In machine learning, we're only trying to estimate some future observable thing. We're not necessarily going via the physical theory, we're going via whatever kind of mathematical relation fits to relate what we initially saw with our final observations. And then we match that experience of the past to some new situation that we see today. It's a different approach, but it builds on and overlaps with sampling theory statistics, and machine learning these days also uses various Bayesian approaches. Okay. Why then does our course concentrate on sampling theory statistics, which as a shorthand I will probably just talk about as statistics in this course? Answer: sampling theory statistics is very common in industry and medical research. Partly that's because of its emphasis on objectivity, not allowing your previous opinion to colour your conclusions about the effectiveness of some method or drug. Partly it's because sampling theory statistics are quite scalable to many practical problems when we do have the ability to do repeatable experiments. And partly it's because sampling theory is able to do hypothesis testing and rejection when we have a complete lack or radical uncertainty about what's going on, or a complete lack of prior information. That's useful in industry where we probably don't have multiple complete alternative physical theories about some new industrial process. We just need a way to do the process as repeatably as we can, and have a tool for hypothesis testing or for estimation to see how well we can improve this process without worrying about having textbooks and textbooks of background prior information. So we are going to use this sampling theory statistics to study how to answer questions when the conclusion involves uncertainty. Before we do that, we need to review, where does uncertainty come from? And this is actually not just a question affecting mathematical scientific data analysis, it's a long-standing philosophical question. So we have here a cutout from one of my favourite paintings, Raphael's The School of Athens in the Vatican. In this somewhat anachronistic painting, all of the Greek philosophers, the famous ones from a few hundred years, are standing together or having conversations with each other, and two of the important ones for this question, what is uncertainty, are Parmenides of Elea and Heraclitus of Ephesus. Heraclitus comes first, so his idea of uncertainty is that we live in a world of change. He had a phrase, everything flows, and another saying, you can never step in the same river twice, because it's not the same river, it's changed. And you're not the same person, you've changed too. So for Heraclitus, uncertainty is a physical thing. We do not know what the future will bring, and we can't. It's fundamentally indeterminate in some way. And this gives a physics idea of uncertainty. It's like the question, will a unstable nucleus undergo a radioactive decay if we watch it for some period of time? Officially it is indeterminate. If we did the same experiment again with an identical nucleus, it wouldn't necessarily do the same thing, because it would have the same indeterminacy about what it will do in the future. Parmenides of Elea I like a bit more. He believed in he was a determinist. He believed that the future was essentially determined by the current state of the world, because everything has a cause, and if we knew the current state of the world, we could see what future would be caused. So for Parmenides, there is more epistemic or informational uncertainty. Uncertainty here is simply caused by a lack of information, so that if I go and ask somebody to tell me what day of the year is their birthday, I have uncertainty about that before they tell me, but then if I were to repeat the experiment and I were to go back the next day and ask the same question, I really shouldn't have any uncertainty. because my lack of information has been resolved, and the repeat process of asking the question. Therefore, if I'd been paying attention, I should be able to tell you the answer before I get them to remind me. So there are those two kinds of uncertainty. And these views of where uncertainty come from strongly affect the interpretation of probability, because in this course, probability is the thing we are using to deal with situations that have uncertainty. So if there's two kinds of uncertainty, I need to have a view of probability which is either based on one of them, or preferably it's profound enough that I can cope with both kinds of uncertainty. So you may come across these two definitions of probability. The frequency interpretation is that probability is the long-run frequency with which an event occurs in repeated trials. So, for example, in nuclear physics, we could imagine an unstable nucleus has a 0.4 probability of decaying during a particular observation period. During one such trial, a nucleus might or might not decay, and if we repeated the trial with an identical nucleus, we might not get the same result. Nonetheless, there is a physical property, we imagine, of the nucleus, its propensity to decay, which causes the long-run average proportion of decays to tend towards 0.4, as we have eventually a very large number of attempts at observing this process. With propensity probability, we are imagining a physical parameter, so that we can imagine if we applied a very high pressure to a block of the radioactive material, then we might observe a change in the long-run average rate of decay, and we could collect lots of data, we could do some statistical tests, and we could identify whether or not we think we had changed the physical parameter. So applying a very high pressure, perhaps this makes it less likely to decay. So we might say that our probability has gone down from 0.4 to say 0.38, and we could do some sort of test on how confident we are that this is a real decrease. Okay, so we're looking at a physical thing there. The other interpretation of probability is the informational interpretation. This is not a physical property, this is a property of my state of mind. Informational interpretation of probability is my degree of belief that a statement is true. For example, when I am making a particular type of cake, I might weigh out the ingredients, and I might do so with my characteristically careless attention to detail in the kitchen, and then when I'm in the middle of the cake, I might have a degree of belief, a probability 0.75, that my cake will turn out successfully. But this is purely my own state of mind. A more attentive cook who was watching me doing this process of making the cake would simply know whether or not I had weighed out the ingredients correctly. And assuming that cake success is purely down to weighing out ingredients correctly, the more observant chef would not have a situation of uncertainty. They would either have simply knowledge that it was true, or probability 1 that my cake would be successful, or probability 0 because they know I'm making it wrong. The informational interpretation is natural for many kinds of processes like cooking or industrial processes, but nonetheless we can apply the frequency interpretation as a model to it's a stand-in for my state of uncertainty. If we apply the frequency interpretation to my cake making, then we're not actually believing that the cake that I'm in the middle of making is in some indeterminate state, and some future quantum event will cause it to either be successful or not. That's not what we believe. Instead, the propensity probability for the cake to be successful is just standing in as a model for my lack of knowledge. If you want to imagine it applying to something in the future, you can think of the propensity probability as applying to my future state of mind when I turn out the cake and discover if it's good or not. My state of mind you can imagine as being a bit like a radioactive decay. I don't know what's going to happen until I see it, and then it becomes true or false that the cake is successful. if I buy a better set of kitchen scales and I actually start to use them properly, then the next time I make a cake, perhaps I will have a higher degree of belief probability, say 0.9, that my cake will turn out successfully. This is, again, if you can imagine this as a physical propensity probability which is standing in for what will happen in the future to my state of mind, except that because my state of mind is more precise, the propensity probability I'm using to model how the future determination of the cake success is going to be revealed to me is going to be more favourable. Okay, so we have these two interpretations of probability. In this course we shall be using the frequency interpretation of probability, and we'll be using it as a useful model for processes. The algebra of this probability is something we will look at in more detail next time, something that we shall look at in the future.